in the delay. Thank you all for coming. And today we'll have Abbas's talk. How do I move to the yeah? And he'll be talking about that. It will be a continuation of yesterday's Dhruva's talk. And I hope you guys enjoy. Let Abbas take over the guys. Thank you. Yeah.
So, hello everyone who's made it on a Sunday morning. Uh, I am going to talk very briefly about information theory and some of its basic ideas. And it's more of just you take the intuition home and then you apply it to a variety of scenarios and thought experiments in your head. Uh, I titled my talk A Tale of Two Labs. Uh, it, so, this lab scenario, usually, so I have, there's one lab which has PI as Alice, and there's another lab which maybe a bit okay. So there's a Alice got some funding, made a bigger lab. And gave some to Bob. So this, can you see my labs, people already? Good. Yeah, so this lab is controlled by Alice. This is Bob. And usually this lab scenario is a good way to understand information and the consequences of information. So it's used mostly in information theory to understand what is information. Good. So I'll assume that each of these labs control a two-dimensional quantum system. I represent it by a sphere here. It's like the block sphere or the sphere you met yesterday. But what you did was you didn't need all the parts of the sphere, and so Dhruva introduced that there's states that lie on the surface of the sphere. But in information theory, we have to deal with noisy states, that is, states which are not exactly, we don't have complete information about those states. So we have to go to a formalism of what's called mixed states. So let's start with this thing. Cool. So the first topic of today is states and ensembles. Now, usually the states you met yesterday were described by a vector, and states are usual quantum mechanics are described by vectors. And but what happens is that if you, let's just say Alice has a box, and what she does is she has a coin, she tosses the coin, prepares a state 0 to get 0. This is a label for the state. If she gets a hit, and prepares the state 1 if she gets a tail. Now this thing is like a ensemble of states, right? Because with half probability, or if the coin is minus, with p probability, you prepare this state 0, and with 1 minus p probability, you prepare the state 1. Good. Now, after preparing these two states and tossing coin multiple times, what she does is she puts this into a box. Okay. So the box, the state of the box, if you pick it, there are multiple quantum systems in the box, and you pick one of these quantum systems. Now, how do you describe this quantum system? You can say that it might be in 0 with a probability of 1 minus p, or it might be in 1 with a probability of all b. Yes. Now, this is a good description. That there's no problem in using this description. But let's just consider the notion of expectation values. So let's just say Alice, after taking the system out, measured some observables. Everybody is familiar with observables, right? Now, we introduced the notion of observables in operators, Hermitian operators. So measurements in quantum mechanics are probabilistic. So what you do is you make a measurement multiple times, and you get the expectation value of the measurement. This observable for a two-level system can be measurement along a 0-1 basis or something of the sort. And this is given by style the observable side. Good. Now, let's just describe that this state I describe as state of this thing you pick. I describe it as, let's just say, some state labeled by sigma. So what will be the expectation value you'll get after measuring this state? This is like you are given the state sigma and you're measuring m. This is my notation for it. So it's clear that with the probability you get heads or 1 minus p, you get the state 0. Right? With so the expectation value of the state 0. Plus, with probability p, you get the expectation value of the state 1. Right? Because the state was prepared, this ensemble or the collection of states was prepared in such a way that each time you got heads, you prepared one state, and each time you got tails, you prepared the others. The expectation values, if you pick a state randomly from this, follows that with 1 minus p, you will get this state and hence this expectation value. With p probability, you get this state and hence this expectation value. This is clear. Now, what we do is we do something interesting to write this expectation value as place of I know it might be confusing to some of you that what are we doing here? Here it is. Uh, Everyone knows what the race is. Some of the time. Some of the time. Cool. Everyone knows what this thing means. 0, 0 and 1, 1. Out of order. So be aware. Or everyone online is aware of such a thing, right? Good. Now it's your homework to verify that this thing is equal to the expectation value. You just take it for granted now. But this allows you to move because trace is a linear function. This 1 minus p can go inside and you get something of this form. 1 minus p. Good. And I call this part as something which is this part I call as group or the this part. This is a operator. This is a matrix if you want to see that. This is a matrix right now. Good. And this is a product of matrices. The observables are matrices. This outer product gives a matrix. We are summing into matrices. Good. So if I will just write down this outer product ones to vector so that no one gets confused. So if for arbitrary to vector, so if you have vectors psi given by a 0 plus b 1 and you have a vector psi prime given by a prime 0 plus b prime 1. What you have is the outer product of psi prime psi is equal to a e prime a e a prime a prime b e prime a e prime. Good. So entry wise we multiply and construct this matrix. Or 0 0 the outer product is 1 0 1 0 1 0. For 1 1 we'll get the other 8 as good. So this is a matrix. We call this. So effectively what we've done is we've encoded all the information of this state in this operator row. Because this operator row itself gives all the expectation values possible, right? All the expectation values are the considered of the observable level. And this row quantifies everything, every expectation value of any state you pick from this one. Good. So this is called a density matrix operator. Something you speak. What do you want to call it? Okay. So good. So now we'll So this is expectation value. However, single shot means you measure once. So then you get some probability of each outcome happening, right? And the probabilities of, let's just say, if you have a observable, if you have a projector like he introduced yesterday, if you have a projector PM, then the probability of getting the outcome M is given by this thing. Should I explain this? If there's doubt, there's no. This explain now? Yeah. Good. So I think it's more of a writing the way of the bond rule you are calling, right? Bond rule. How do they calculate probabilities for a point? So if you measure something, how do you calculate the probability of what's going to happen? Okay. So if you are measuring, let's just say an observable M. So it will have, it's a Hermitian operator, it will have eigenvalues and eigenvectors. So you decompose this as the eigenvalues and eigenvectors. And these are the set of projectors I think Dhruva introduced tomorrow, right? Yes, yes, sorry. Yes, yes. Physicists have a relative version. Good. So now the bond rule says that if you measure this state sign, then you'll get an outcome eigenvalue M with a probability given by sign. This is the point. Cool. Now what I do is I just write it in the following form. And this I call PM. Good. So probability of getting an eigenvalue or the outcome M is given by this thing, this data. But the same argument works, right? Because PM, you can replace F by PM. And you get the probability of you getting an outcome is given by PM for this data. You have M here, you just replace this by PM. So everything is the same. It's a linear operator here. We'll get just the PM. You get just the PM part. Good. So this is the probability of getting an outcome M is given by this thing, and in the state we prepared, it's given by trace of PM acting on the row. The density matrix also allows you to calculate the probabilities of it. That's not a problem. I know it's sort of a math, but it's okay. We don't really need, we just need to know these concepts and you can just figure out when you get back. But you just need to know the probabilities and summarize the results. The probability of getting the eigenvalue M is also completely specified by the density matrix. If you have on this type of preparation, that. So the density matrix contains all the properties of the measurement. Yes. Yes. Now, probability and probability have been traced in that. Now it's time density matrix. Can you repeat the question? So the calculating thing we have the structure of the mathematical element takes this Yes. Yes. So how is the because every measurement is in this book. Uh, you have an observable and you have a set of eigen this uh, eigenvectors and eigenvalues, and every measurement is gets you an eigenvalue and projects it to the eigenvector. That's it. We will be more concerned about these probabilities instead of what happens to the point of the system. Now, if I did follow such a procedure and I just prepared state 0, no matter what happened, you get the density matrix equal to this. Good. And the expectation value of the observable. And the expectation value of the observable is this, and this is what you expect. Good. So these type of states, which do not lie in this probabilistic picture, are called the pure states. Right? These are the usual states you work with in here. Pure in the sense that they don't have this sort of probability attached to each or no. Cool. These are like they're not probabilistic. You know what is there. So these are called the pure states. So I'll erase this part if someone else does. Good. So I'll summarize what I have done. So we have state called now they prepared this operator rho. Now satisfies the I'll just write out these properties and also satisfies that it's positive. I'll explain each one of these things. Cool. So we looked at this sort of a state. 0, 0 with probability 1 minus p. We have 1. Yes. Good. So this thing, if you take the trace of this quantity, if you write this down in a matrix form, what you have is 1 p and 1 minus p, 0, 0. Good. Because this means that you that it was 1 to 0, 0. The trace of this is 1. And this notion that the trace of rho is 1 is equivalent to the statement that the probability must sum to 1. So it's what? P and 1 minus. You're taking 0. Sure. And also you are going from complex. So I don't understand the domain. How they are doing saying there is a function that makes something from zero from then head data can I be two as B to take any n vector to another. Clearly, that's exactly what it is. It takes the specific case cubic case. The row in the matrix. It takes the two element vector, two element complex vector, two element. So that is equivalency of matrix because of linearity. But we are also look at figures. Matrices are not between yeah, and good. So this positivity condition comes due to the fact that these expectation values you want them to be greater than equal to 0 because the real not the expectation values, the probability. So this is the probability of getting an outcome M, right? Probability of getting an outcome M should be always greater than equal to 0. That's not a debatable. You cannot have negative probability. And this is the definition of for all PM. This is what I'll call the operator. Good. Now we are so any perfect map or matrix operator which satisfies these limits. It's called a density matrix, and it can be understood as a preparation which was like you have some states, you prepare some with the probability P, some with the probability 1 minus P, and you put it in the box. Good. So now we have, I think, mostly done with. Now using this, we complete our picture of the block sphere. That is, we fill up the block sphere now. So yesterday we were looking at the surface of the sphere, right? Because yesterday all we had access to was the pure states. There was no mixed this density operators and all of this. There were only states of this form. And in the density matrix formalism, these become density matrices like this. Good. So now, if you have a matrix, I know it's a 2 cross 2 matrix because I have taken it in this way. Everyone knows what poly operates. No. Okay. So I'll just introduce. So 0, 1, 1, 0. Sigma 1. 0, 1, 0. Everyone knows. These are the 4 poly operators. And if you want to check, you can check that these are linearly independent. That is, you cannot write any one of them in terms of the other. Good. So these 4 operators form a basis of the set of all 2x2 matrices, right? Because these are linearly independent. So these matrices are a vector space. Vector spaces everyone is aware of, right? So these four things form a basis of the 2x2 density matrix. Matrices, 2x2 matrices. Good. So I can look at this 2x2 matrix by expanding it in terms of the poly operators. So I'll just call this as sigma 0, sigma x plus sigma y, sorry, lambda 1 sigma y plus lambda z sigma z. Good, this is not a problem. I just expanded the 2x2 matrix in the with some coefficients in this polyoperator. Good. Now we know some certain things about this polyoperator. All of these have a trace of this, except there. Good. So if I take the trace on both these sides, you get 2 identity has a trace of 2. You get 2 lambda. The rest have a trace of 0. Yes, lambda naught has to be half. Yes. So 5, 2, and so this is like lambda naught is good. So we have figured out lambda. What other condition is there? It's that this has to be still a positive. Okay. Now, positive matrices in general are also Hermitian. I'm not going to prove it, but I'll just write it down as this thing implies that rho and equal to rho. Now, if you take the dagger of this thing, identity dagger is itself, adjoint of the identity itself. What's everyone knows what the dagger is. Okay, good. Yes. So, what's sigma x dagger? Same. You want to check? You can check that all of these have the same dagger. So they're what's called Hermitian matrix. Good. So if I apply a dagger to this thing, 2 plus 2 dagger, you get lambda naught identity plus. What happens if you star a complex, dagger a complex number? Convolution. Plus star sigma y plus lambda star sigma z. Good.
If you're continuing to broken in the base of our identity matrix representation, we have a set of conditions.
Yes.
So we could have taken the basis to be continuous non-identity.
Yes.
So is that some property of the density matrix that makes it represented? So the way we say operators, you are using
The density matrix has positive eigenvalues.
sorry.
The density matrix has positive eigenvalues, right? They're automatic variable.
And it has to be
Yes. So we know that this dagger, because we know it's Hermitian, this dagger is turned into itself. And we are expanding in the same basis effectively. So these coefficients must be equal, right? Because there's a unique decomposition in the basis. So lambda x star equal to lambda x, lambda y star equal to lambda z star equal to. This means that all of them are real. Star of a number is equal to itself implies that the number is real. Good. These lambda x, lambda y, lambda z are real vectors. Good. So I'll just do this. So we figured out what lambda naught is. It's ideally half. These things are real. So what I do is I write lambda x, lambda y, lambda z as a vector which multiplies the Pauli matrices vector. This is the usual dot product. This is a notation. This is just a simplified notation to write this. This we know is a real vector. As in it has three components and all of them are real. Good. So I write this down as lambda not sigma. Lambda is this whole vector, sigma is this whole vector. Now the only condition left is the positivity. We have not yet imposed the positivity condition. And once you impose the positivity condition, I'm not, it's going to be a sort of a lengthy proof. So I'm just going to say what the positivity condition implies. That lambda must be smaller than equal to 1. Good. I know it's not very clear why this should happen. But the positivity condition implies that lambda modulus, this is the norm, what they call lambda x square plus lambda y square plus lambda z square root smaller than this comes from the positivity condition. We can talk later after because there's already not much time to cover a lot of these things. Good. Now, once we have access to this vector, which has a norm smaller than equal to 1, we construct. This is a condition for a sphere, right? If you have these, if you define the coordinates in this way, this is the condition for a sphere, right? This is the radius of the vector. Yeah, right with the surface. Not the surface, the inside and the surface, right? Small and big. So good. So what picture we have is all these states of 2 cross 2 matrices which satisfy these conditions lie inside this sphere which we have just constructed. And this is x, y, z. And what we can see is that if lambda is equal to, this modulus is equal to 1, we can show that all these states, pure states, if you square this thing, you can see that it still remains this thing. Good. This is the defining condition for pure space actually. And we can show that if you square this thing and equate it to itself, this modulus is 1. Okay. So modulus 1 means on the surface of the sphere, lie the pure states. In the inside of the sphere, lie the probabilistic mixture of pure states. right? The states we started P with P probability we have to so that why the outer product is same. And when we say all to the states will have this. Yeah. So if we use this condition here, that this density matrix square is equal to itself, we get mod of lambda. So good. So this thing, so the surface includes all the pure states. And what about states of this form? So if we have a pure state here, I call it psi inside. And the pure state here, call it phi. Any probabilistic mixture of these two things. Any probabilistic mixture of these two things lies on the line connecting these two. So if P is 1, this part is 0, you get this bit. P increases, you move along this line. And you reach till here and P is 0. Good. So this is so this picture is very helpful because it helps you understand what the geometry of the states of the 2x2 qubit system is. And so this is a convex set. Sorry. This is convex set. Convex means that if we take a probabilistic mixture of two things in the set, or you just draw a line joining two things in the set, the line lies inside the set. There are sets. Yes. There are sets which do not hold this property, like a set of this form is not convex. The geometry is not convex because if you take this point and this point, so this convexity is a very important property of states in quantum information. It's used everywhere. Not just two cross two things. But this picture is there. So now we can look at some. So this picture helps you look at some basic ideas and information. Good. I just erase this part now for a quick comparison with classical bits and classical information. So what are the classical mixed states and pure states? So classically, you always here you have bits instead of two-dimensional quantum system. Bits 0, 1. Good. But these are pure effectively, right? Because you can know everything about if there's a state 0, you know that you don't have a confusion key, what will you get? Right? Like so this 0 in classical physics is equal to a pure state in this picture. Good. So what will be the set of mixed states in this classical picture? That's a question. So in classical physics, like Dhruva introduced, we have probability distribution. Good. So probability distributions are, let's just say there's a probability distribution which will tell you the probability of getting 0 and the probability of getting a 1. And these must sum to 1. Good. This P is called a probability density distribution, whatever you want to call it. Now, what will be the pure states? Pure states will be of this form, or P0 equal to 1. That is, you have all the information you need. There's no probability in it. Because it's certain that you have zero. It's certain that you have one. Good. And what will be the mixed states? The mixed states will be all other distributions, which are early convex mixture of the probability distribution. This probability distribution plus 1 minus lambda. The other probability distribution. This is the probability distribution where you have 1 is certain. This is the probability distribution where 0 is certain. And the convex mixtures of these probability distributions are all the probability distributions you have. Yeah.
Like you know, general question like can you talk a bit about the why convex will keep coming up with all kinds of cases?
All kinds of places. I don't know. I mean, I know why they come up in quantum things, because you have probabilities involved. But all places where you have probabilities involved, I think there will be a notion of convexity, right? Because the probabilities sum up to one. Yes. Good. This picture, and I mean this is just a one line thing. This is the more complex set than the classical. This allows you more power. If you think very naively, it allows you some more power over information from information. Good. Now we have cleared states and ensembles. So we'll just move on to a bit of information theory in the end. Yes.
But so consider 1 minus 0 to 0 and 1 plus 1 minus 0 to 1.
Okay.
And let me take the density.
Yes.
And also let me take the density matrix of half 0 0 plus half 1.
Sure.
So both of these, if I measure it, I will get half the number of times I get to or half the number of times I get. What is the difference between is superposition just probability and elimination of?
So I'll rephrase this question. You have a density matrix, 1 given by 0 plus 1 by 2, 0 plus 1 by 2. And you have another density matrix given by 0, 0 plus 1. Question is, how do we distinguish them? That's the question. Hardly different. They're different as density matrices because this will have terms. If we expand this out, we get the terms 0, 1, and plus 1, 0. They are different as matrices at least. That are quite clear. That's a clear thing. Now the question is, if they are different as matrices, which I will answer in the next part of the talk, then you have a measurement to distinguish. That's a note. Here, what you do is, if you calculate the probabilities of measuring the sigma x observable on both of these things, the probability of measuring sigma x, the observable, I think the expectation values of these two expectation values are also different. So you take the state, this thing, trace, rho, and trace rho 1 and sigma x. It's a homework question for you. These two things are not used. So if you have designed an experiment to measure sigma x in each of these two things, you'll be able to see they are not distinct. They're not, you get different expectations on them. Good. Technically, they're almost the same. Almost. What's almost? They are same. Same. Why? Yeah, I mean, for some observables, like sigma z, get the same answer. That can happen for one observable, but it will not happen. If it happens for all observables, then there must be the same. Equation needs to be same for all observables. Have sigma any sigma. Okay. Why do you say that? So I will just tell. So that's why I asked this. They look very similar, but they're very different. Cool. So I will just tell you, if you measure sigma x in this observable, if in this state, you get only one answer. Okay. The probability of getting the outcome 1 is 100%. There the probability of getting an outcome 1 with sigma x is half. You get an equally probabilistic mixture of 1 and minus. Good. These are not the same thing. And these can be distinguished using some measurement, at least some measurement. This is an important notion in information theory, that because transferring information requires distinguishability. Cannot, if I want to send someone a bit of information, that is, I want to send them either a 0 or a 1. I want the 0s and 1s to be distinguishable from them as possible. So if I send them row 1, row 2, and they are not distinguishable under any measurement, I've sent no information. They cannot access any information. So, but I say that measure in sigma x, so that if you get this expectation value, you infer that I have sent you 1. If I send you row 2, you infer that I send you 1. So this is an important concept, and I'm coming to it. Yes. For all. Yes. The states are the same. Yes. Cool. So now let's just come to the Alice and Bob, which we started with. So we had, so second topic of today's discussion is state discrimination. This is a basic task in information theory, that you have two labs, a Alice Bob. Alice wants to send some information to Bob. One bit of information. She wants to send a yes or no answer, or something of this. Good. Is it raining or not? Is it have you eaten food or not? That sort of an answer. It requires one bit of information, right? It's yes or no. So let's just say she prepares. Now let's just say both have access to only classical systems and classical measurements. Good. So classical systems, we know what the classical mixed states and pure states look like. Pure states are the probability distributions which are certain. The mixed states are the probability distributions which have some probability of getting a zero, probability of getting a zero. So Alice wants to encode. So let's just say Alice sends a bit 0 or a 1 to Bob. Now there are, let's just say, anniversaries. E is usually stands for Eve. Who doesn't want Bob to know what Alice has said. So he doesn't want Bob to know if Alice has eaten food or not. So what he'll do is he'll corrupt this information. He'll apply something to this information. He'll corrupt what Alice has said. Good. So the initial probability distribution, so if Alice sends P0, what he does is he corrupts P0 to some other probability distribution, lambda 1 P0 plus lambda 2 P1. And if Alice sends P1, this is problem. He corrupts this thing to 1 minus lambda 2. Good. Now this thing, so if you take the original probability distributions, there's no mistake Bob would have done, right? Because this is certain that Bob will measure the outcome field. This is certain that Bob will measure the outcome one. Right? But now the outcomes are also probabilistic. Good. So Alice or the Bob needs to distinguish between these two things. Now, what's the corrupted information? Good. So what Bob does is that Bob tries to obtain. So Bob will do this task, right? If he obtains 0, he'll say he'll infer Alice and 0. Right? That's the best we can do. And if he gets 1, he'll infer that Alice said 1. But what's the probability of making the right choice? It's lambda 1, because lambda 1 gives the conditional probability that you had 0 and then at the final thing you also have 0, right? So Bob makes the right guess with probability of lambda if the state Alice started with is 0. And similarly for y, it's 1 minus lambda. And just take the average probability of guessing correctly. Good. So this is the average probability that Bob guesses correctly what happens. Good. How does 0 correspond to lambda 1? Can you repeat? So you're saying that originally P0 was 0, but now it's changed to lambda 1 P0. Bob inferred that. Bob inferred using this equation. So this lambda 1 gives the probability that finally you have 0. It is and started with 0. Probability is 1 minus lambda P. Not would be 0. I don't understand. Then, go on. Yeah.
T naught would be then 0 and lambda 1 T naught would cancel out. T naught to 1 minus lambda 1 equal T naught. Instead of just giving what just clear so why would it be lambda 1?
Where?
Repeat it again.
Here?
There, just say lambda 1 for the why.
Right, right. So this is the probability that Bob measures 0 given that Alice has measured 0. Good. This is the probability that Bob measures 1 given that Alice has measured 1. So we can write this in general terms. So what will be the probability of getting a 0 given that Alice has sent a 0 plus probability of getting a 1 given that Alice has sent 1. And what we do is we know that P 0, 0 1 plus P 1 0 1 1 is equal to 1. Okay. This should be 1 because either we'll measure 0 or I will measure 1 given that Alice is saying. Good. So we replace this thing by half of P 0 0 plus 1 minus P 0 1 1 we get half 1 plus P 0 minus P 0. Good. Now, what we can write this thing as 1 plus P I'll explain what this thing is. I'll just tell what it's called. It's called the trace distance between these two probability distributions. So this probability distribution, I mean that what probability distribution Bob had access to finally, if Alice had sent 0. And this is the probability distribution Bob had access to if Alice had sent 1. And there's a notion of how distinguishable these two probability distributions are, which is quantified by this quantity. It's called the trace distance. And so if this thing is 0, if they're not distinguishable, they're the same, then the probability of guessing becomes half. Right? It's like a random guess.
So your probability of getting directly is half.
Yes. This you can at least guess how. Yes.
So in this case, are you thinking that Bob knows how he will messing with the code or not? Are you assuming that?
No, no.
But in that case, why not this thing? Make it complete process.
Yes, yes. You can do that. It's not 0 because what happens is that you can still distinguish these probability distributions, right? So what it's like best pocket.
Oh,
It's not the
so this is continuous, set of information to every just one data. So he's saying let you compute every one to zero and every zero to one.
yes,
For doesn't know that is one thing.
yes. But he doesn't know, but he can. The point is, this is key. What the best Bob can do about this. So he can still distinguish zeros from one, right? I know he'll get the wrong answer, but it's the so then he tries to say he, if I get a zero, then Alice must have get a one. It's the best. It's the best thing Bob can do.
Who's Bob?
Yes.
Here that's not the one.
Yes.
The point is even in the opportunities for one and two, where there is a complete two. Even then the particular is not whether any number. At some point it is a question of whether Bob gets exactly what I am create or not. But also whether Bob can create the two states. If Bob receives half zero half one, regardless of what A is, then there is no point for Bob to do any of this. He's in the other case where let's say that Bob and Alice can set up a thing where Alice is the first time I use this. Then Alice can sound. And if he has switched the two then Bob Gulati says that yes, what I have you know that and that question is enough for me to set the set whether zero is eating or one. But if Alice needs to pick up in such a way that it's always not zero or one, then there's no question.
It's the best you can do. It's not like he, exactly what he said. If Bob, if the probability distribution become the same, then there's no distinguishability left between the probability distributions. But if Alice just flips everything, then you can still distinguish the initial information, right? There is a possibility of getting the initial information. If the probability distributions become the same, there is no possibility left of getting the initial information. That's sort of a picture. What we have. So this thing is equal to half P I is from 1 to I go is from 0 to 1. So if you find this out, you get P 0 0 means P 0 P 1 plus P 1 0 P 1 1. So this thing, if the probability distributions are the same, then these two things are zero, right? Because probability of getting is zero and the probability of getting zero, and both the probability distributions are the same. Yeah.
Zero and one downstairs.
Yes.
Zero down. Right?
What is P? I just these are just label for two probability distributions. You can call them X, Y. X, Y. So you can check that this thing is true, this equation. I don't have the time to completely go through it, but so this distance between these two probability distributions uh, quantifies how much, what's your how much probability you have of guessing maximum probability you have of guessing correct. That's all. So this thing has the operational meaning in this. Operational means that you can interpret this as a some protocol of information. Good. Now these are the classical. This is the classical things. Now Alice and Bob have heard that quantum is in the market, and what they have heard that quantum is better than classical in almost everything, and people are pouring money into it. So let's just try doing this sort of a thing by using quantum system, and let's see what advantage we get by using quantum. Good. So Alice now has access to quantum system. Quantum systems are all the states of inside the blocks. For us, at least, they are all the states inside the blocks. Alice again wants to send a bit of information, but now she is using a quantum system to encode the bit. So if you have, let's just say, if she wants to send a 0, she prepares a state row 0. If she has a 1, she prepares the state row 1. Good. Now, if you prepare state row 0, row 1, these are like probability distributions only. In just we modify one and modify. And she sends these two things to Bob. Bob starts to distinguish between the both of the probability distribution, quantum states. So what Bob can do is apply a measurement. Okay? That's the best he can do, and the measurements are described by observables, which have this sort of a decomposition. Cool. Now, what he applies is he applies a 2 outcome measurement. That is, he wants to distinguish. So if he gets an outcome 0 in the measurement, he says that Alice sent a 0. And if he gets a 1, he says that Alice sent a 1. Good. So this 2 outcome measurement is of this form. So these, you have two projectors because 2 outcomes. Good. 2 projectors, 2 outcomes. And the probability that Bob guesses correctly is given by, if we had a state rho naught, he wants the outcome 0. Right? And this is the probability of getting an outcome 0 if we had the state rho naught. Plus trace rho 1, and he wants to maximize this probability that you get the outcome 1 given you have the state rho 1. Right? This is what is a generalization of what we had in the classical method. Good. And this is the average of these both probabilities. Good. Now we know that P naught plus P1 equal to the identity because they are the complete set of projectors. So we can use this thing to replace P1. We'll get rho naught P naught plus trace rho 1 identity minus P. Good. This is also equal to trace rho naught minus rho 1 P naught plus trace of rho 1. What's the trace of rho 1? It's 1. It's a density operator. Now, what effectively Bob has to do is to optimize over all the measurements you can perform. This P naught is what Bob is performing, right? So you want to maximize this over all the projectors P naught. This will be the best thing Bob can do. Like this is the best probability Bob has of guessing correctly. Now, again, it's a very long proof, but I'll just give the, I think the answer is that there is a quantity called trace distance again, but this time it's between two quantum states. Yes, states density operator. Yes, I'm just referring to everything as the same density operator. Now, one. This quantifies how distinguishable these two things are. This rho not rho one. And so looking at it this way, wouldn't you say that if the velocity is the half and the central level quantity, aren't they like similar to the yeah, I never said there's something better about I mean, you can see the thing is that it lies between half and one. That's for sure. Right? That's not the problem. So it's like just comparing the two processes and seeing what each of these two things gives. It's nothing about the advantage or the disadvantage. So this thing, rho r minus rho 1 is equal to, for the case of density operator, it's equal to the sum of the eigenvalues of this thing. So, it's equal to the sum of the modulus of the eigenvalues of rho naught minus rho. It's a definition. I mean, and you can see that this definition is equal to this thing. Right? It's a hard thing to see, but I'm just saying this thing is true right now. Now, if you have density matrices which are just diagonal, right? If they're only diagonal density matrices, they effectively act like probability distribution. So if you calculate this for only diagonal density, this distance for diagonal density matrices, you'll reduce it back to the classical case. Why? So if you have two diagonal density matrices, lambda 1 minus lambda minus P 1 minus P. Then we this thing. let lambda minus t mod plus 1 minus lambda minus 1 minus t mod. This one cancel out. Plus this again 2 lambda minus t. This is what we can see. So effectively, diagonal density matrices, if you take all the diagonal density matrices, they are a set of classical polynomials. There's nothing more about it. The only thing comes due to the non-commutative fields. So if there are off diagonal terms, and quantum things are off diagonal things. Off diagonal things will happen. Okay? That's the brief. That's a explanation of what's different about quantum things. But cool. This was the, I think this is, I think, the first task people introduce in what's and how to think about information. And I don't think I have time. So I'll just give a brief conclusion to what we have learned. Uh, yes. Good. So we learned states, ensembles, and how quantum systems can be represented as state mapping. Then we looked at information distinguishability. I wanted to look at something called channel theory, but I don't think we have the time. So thing is what's information now? What's the general idea? Information is something which we encounter everywhere, but we more of have an intuitive understanding of what information is. Shannon in I think 1950s made a more mathematical understanding, made it more precise to say what is transferring information, what is so he looked at only the classical case because there was quantum theory, but nobody really cared so much about quantum theory. They looked at the classical case, and he was looking at this task of you can have Alice, Bob, and Alice had some information source. So the information source can be a physical person or a non-physical thing. Like information source in the sky and is it raining or not? And it's a random process. It's not. There's some probability it will rain. There's some probability it might not rain. And the probability that it's not half of also. It's like 90% it's not raining, 10% it's raining, but Alice doesn't know beforehand what's raining. So at the end of, let's just say, each month, Alice has to report to Bob how many times it rained. So is it raining? Is it not raining? It's a question of one bit. It's like one yes and one answer. Is it raining or is it not? So Alice needs to send So let's just say she has to report every hour of every day. Is it raining or is it not raining? So it's a string of bits she has to report, right? Is it raining? Is it not raining? Good. She has to report a string of bits to God. And all these strings have probabilities attached, right? So probability that it didn't rain all the 30 days at each hour of the day will be probability of raining. So let's understand that each of these things are independent. Right? So it will be p to the power. P is the probability of rain, not raining. So it will be p to the power how many string bits there are, right? And if p is right. So now thing is the Shannon was looking at the question how is it best to compress this information. So how much information does this thing contain? That is three bits of it. So if the length is n, you're saying so how many people ever define the rate? And yes, you guys found out that define the is how do you define where the ones are? How do you define where the ones are? I'll tell you. No, but to tell the location of ones, you need bits. The only thing you want to send is bits. Oh. Okay. So you cannot tell where the ones are without sending any. So effectively, if you're looking at strings of length n, so what happens is that let's just take this thing. So if there are 4, so let's just say 0 occurs with the probability p, 1 occurs with the probability of 1 minus 2 in this string. Good. So probability. So let's put this in concrete terms. So the p is, let's just say 1, 4, and this is p. So if we have 0, 0, 0, what will be the strings which will have the most probability in this? If 0 occurs with the probability 1, 4, and 1 occurs with the probability 1, 1, 1. This will occur with the most probability. Then anyone 1, 0. Okay. So the probability of getting 3 1s, 3 1s and 1 0 is equal to 4 times 3 to the power 4 to the power 3 1 1. These are 4 ones. These are 3 ones. And this will be greater than this. Okay? So what we can see is that the most typical strings will be will have number of ones given by 3 by 4 n. If the n is the length of the string. Okay. This is the size of the number of ones in the typical thing. That is the most probable. Good. Now, what Shannon tried doing is that since if we have a large string, if we have a large number of digits, then only the typical strings will occur, and the non-typical strings will have a very low probability of occurring. The set of, let's just say, this is a set of all strings. This is the set of typical strings for a particular n, and n grows. This typical string covers more and more proportion of this. Typical strings are the strings which have ones of ones with this number. This now this is the probability of one occurring. Yes, the expectation value that you'll have these ones will become one. So if the n grows a lot, then approximately we can see that the non-typical strings occur with probability very less probability, right? So what Shannon thought, we don't need to care about this atypical strings, and we just care about what's the typical string, and we just give these to these strings some. We just try to send these strings by compressing, because these are obviously less than the total number of strings. So what he did was he now construct a code. The code looks like, if you have so in the case of 4 examples, there are how many typical strings? 4 typical strings, right? 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 1, no, not 4. Yes, 4. 1, 1, 0, 1, 1, 0. Okay. And you just want to distinguish between these things. And so what you can do is you can just recode these things. So I call this 1, 0. I call it 0, 0. I call it 0, 1. 1, 0. 1, 1. Anytime these 4 strings occur, I send 0, 0, 0, 1, 1, 0, or 1, 1. So I'll taken the information which was contained in 4 bits and reduced it down to 2 bits. Now it may happen that the atypical string occurs. Then you send the string as it is. You can do anything. But the thing Shannon realizes as n grows, the number of atypical strings also is very less. So only the thing is, with most probability you want to send the typical strings. And you can compress the typical strings using this sort of pitch. Cool. So how much compression you can have is given by a quantity called the entropy of this probability distribution, which is defined as P log P plus 1 minus P log 1 minus P. These quantifies the factor. So if you have n digits in the string, this quantity quantifies ns row quantifies the number of typical nsp quantifies the number of typical strings want to have. This gives them how much compression we can do. So entropy comes in this picture. And this has a analogous formulation in the starting of the quantum information theory, where you wanted to compress the information carried by the density limit, which I'm not going into much detail, but that's how it's called Schumacher compression. And that is given by the amount of compression you can do is given by the von Neumann entropy of the state density. Thank you. Yeah, that's. We want the typical states. Typical states are the states which occur with the most crowd. The problem is simple. If all has peak probability, it will be a part of this. Can I not just maximize the probability? Yes, it's so. If you have a binomial distribution, if you take the limit of r large n, then it starts peaking around the expectation value of the binomial. And the expectation of value of the binomial distribution is given by n. Like, it's still don't get how are you, for example, you sending information. You isn't that the applying the same logic in different domains? For example, if a picture, breaking down picture into different sections, and then according to the brightness or the color of that section, you make a different thing of that. And yes. So this thing quantifies what's the minimum possible compression you can do. You cannot go below the compression which is equated by the Shannon curve. And so suppose if you have a paragraph of text, you identify the most commonly used, commonly used sentences. So English in itself comes with a set probability distribution of over all the letters. Right? That's why English can be compressed, because it's not key. Every letter occurs with the probability 1/26. If that happened, you cannot compress anything. If every letter was equally probable, there is no compression possible. But English has, so if this entropy, if everything is equally probable, this entropy is the maximum entropy. That's the. For two things is defined. The two the minimum amount of compression, it's the maximum amount of compression you can do. That is the. So number of typical strings in the limit of large n is given by n times this. That is the log in the log is compared to. Yes, that's the log is compared. This has a straightforward generalization when instead of the zeros and ones, you're sending density into. So you have row 0, row 1, and that's everything. So the one diamond entropy is defined in this way. Finest place of row log. This is one diamond entropy, and this thing quantifies how much you can compress this information. Also, what's the format in the quantum sector? What is format? Form of measurements of what is every observable, any observable. Like, for example, measurement along the axis, or measurement along any axis. No, like think of more. So you have a spin system of time. So you're measuring the angular momentum. Also, we have to identify the probability distribution to apply it. Yes, absolutely. So, Addison usually have some sort of agreement over what they're going to apply. No, so it's quite English question. Doesn't necessarily mean that it has to conform to the probability distribution, like, so after for data, like you build the probability distribution by analyzing the previous distribution. But so you're saying where does you get the P probability of the source? Yes. So I mean, in this problem, it's taken for granted that there exists such a probability. But yeah, this is like constantly to understand how the source behaves. So because if you don't have a priori understanding of what the source is, it's equally wrong. But once you understand the probabilities of what the source is, then you can compress it. So if the source only emits only one type of information, that is certain that it is raining every day, every hour of the day, then you don't need to compress it. You can compress the setting is one. That's the idea. Yes, it's given.
Right, then, thank you, Abbas, for the. Yeah, so we'll be meeting again at 3 p.m. For the would be a semi-formal talk where each of us will be talking about the projects that we did. Of course, Abbas and will be talking about their thesis stuff.
See, I give only one talk.
Oh, you have one. Oh, okay, sorry. Okay. Right, okay, good. So then it's the break. Abbas's talk is not yet finished. My bad. The time is the.
I'm not taking 2 hours. He's asking us to not 40. So we have a 2 hour session. You have 2 hour session. Next 2 hour session. I'll just take 30-40 minutes. See, here's the thing. If there's no one coming, then we'll not know it. Yes. If you think, I mean, it's a simple thing, right? We can stay over with no it, but if no one comes,
Yeah.
and why did we do it? I mean, if it is just a photo of discussing, then we go do it together. But you want to come all the
Anything is there. Prasad, if you're there, great man. If you're not there, we don't know.
So if you guys are not coming, let us know.
Yeah, please. Let us know as in now.
Yes. Like within.
Now only. I mean, like half an hour, where will they contact?
I am. One person said he's coming. One person said online. He's coming.
They're coming up.
Yeah.
Bro, you're on campus only, no?